Welcome. In the previous lectures of this course, we have looked at synthesis problems where area and latency or performance were constraints. In this module, we will look at synthesis problems where power is a constraint. So, we will look at first the scheduling problem when power is a constraint. So, power is consumed by change in register content, use of functional units, buses, etc. Now, if operations are performed simultaneously, power is consumed. What is the measure of the power consumed by a functional unit? At any C step, a functional unit can be active or idle. When it is active, that means it is executing some operation in it. It consumes dynamic power. When the functional unit is idle, it consumes static power. The peak power is given by the C step, which consumes the maximum power. So, among all time steps, the peak power is given by the time step which consumes the maximum power, combining both dynamic power and static power, right. Summation of the dynamic power over all resources and summation over static power over all resources. The C step at which this is maximum gives me the peak power, and the objective of scheduling is to minimize the peak power. Now, we will look at this scheduling problem here. We are given this data flow graph. In this data flow graph requires one multiplier functional unit, one AND functional unit, and two adder functional units. See that this addition operation and these two addition operations are at two different time steps, and hence the same instance of an adder unit is sufficient for operations in this time step and this time step, and therefore we only require two adders. So, this is a schedule comprising one multiplier, one AND, and two adders. Now, we take another schedule in which we take the AND operation to time step 2. When this AND is shifted from C step 1 to C step 2, we may save some power as the multiplier consumes more power than the adder. So, because the multiplier consumes more power than the adder, the summation of the powers consumed by the addition and multiplication here will be more than the summation of the powers consumed by the two adders here, may be more than the summation of the powers consumed by the two adders here. And therefore, when we bring this addition operation from C step 1 to C step 2, it may result in a lower power. This may save power as multiplier consumes higher power than adder, and hence this AND when associated with addition will give a lower power value as with respect to when this AND is associated with the multiplication in the first time step. Now, in the third schedule what we have is that the add operation is shifted to time step 1. Now, this surely increases the total power at time step 1. But what we see here is that now we require only one instance of this addition operation, and therefore, because we require only one adder resource, the static power at each step will be reduced, and therefore, this may result in saving or in reducing the peak power. So, what we wanted to show in this problem is that we can have three different schedules with three different power consumption, peak power consumption values, and hence we can devise algorithms, both optimal and heuristic algorithms to produce schedules where power is a constraint or to minimize power. Right? This was a look at power aware scheduling problems. We will not go deeper into the problems. All the strategies that we have studied can be applied, but the problem remains this. Now, we will look at register optimization for power. Now, base power consumed by the registers is proportional to the number of registers that we have. The active power consumed is proportional to the activity on the registers. What do we mean by activity on the registers? So the number of different allocations that I have on the registers. That means when the bit flips, when the bits within a register flip, active power is consumed, and hence it is proportional to the bit flips. And when does bit flips happen? When the data values in the registers change. So I had a variable A in a register, and then I have put a variable B in a register, and the data within the register has changed. This will affect a certain number of bit flips in the register. When there are bit flips in the register, the active power will be consumed in the register, right? So let X be the power consumed by a register during register transfer. So during register transfer there are bit flips and active power is consumed. And why is the power consumed when it is not transferring? So the power consumed at each C step due to these registers are the summation over X and Y over all registers. Now active power is, as we said, active power consumed is proportional to the number of bit flips that occur. Now this partially depends on the variables mapped to the register. Now what do registers contain? They contain temporary variables. Where do temporary variables come from? From the outputs of operations. The operations, what do? They perform computation on input values, Now these input values for a certain operation typically comes within a given range. The pattern of values that are handled by an operation node is often very similar, or are often very similar over all data inputs. And hence the temporary variables at the output of these operations also tend to have similar values and values within similar ranges. And therefore, if I have two variables, the first in the first I have most of the values changing in the lower order bits. So in this temporary variable, the values of the lower order bits changes more. And I have another temporary variable in which the values of the higher order changes more. Now when both these variables are kept together in the same hardware register, then overall there will be a lot of bit flips when these two variables are kept into the same register, right? Now as with respect to, let us say we have two variables, both for which only the lower order bits change and most of the higher order bits remain same, are all zeros. Only the lower order bits change. So if these two temporary variables are now clubbed together into the same register, we will have higher opportunities of saving power. Why? Because active power is consumed when bit flips happen in the register, right? So the active power consumed is partially depends on the variables mapped to a register. Now two variables are selected for merging based on their average switching power, right? So therefore what do? We profile the operation constraints graph, we deduce the table for average switching power. So we find out when A is merged with B into the same register, what is the switching power consumed, as compared to when A is merged with C, what is the switching power consumed. Likewise, we can have a table containing the switching power for all different types of valid register mergings. And we do feasible register merges to minimize the total switching power. Again, we understand that this can be modeled using a conflict graph, and on this conflict graph we can apply merging and splitting techniques that we learned for register and functional unit allocation when we learned the simulated annealing methodology for register and functional unit allocation. A similar strategy can be, similar technique can be used here to obtain a register optimization for power. We will not go into the exact methodology. The strategies remain almost same. The solution strategies remain almost same. Now we will look at another problem, bus allocation for power. So bus lines are put between registers and functional units. So when bus lines are put between registers and functional units, the muxes, demuxes drop out on the buses. Now if we want to minimize number of bus lines that are required to handle a certain number of muxes and demuxes, the problems are similar to the other allocation problems we learned previously and can be similarly formulated. Now we will look at this formulation for power. So if data is written onto the bus vary a lot, then power cost incurred increases. So power cost is incurred due to switching. Now if we continue to have the same variable allocated to a bus line, the value in the bus does not change. Now let us say we have a 3-step schedule, right, and variables are put onto the bus at each step. Let us assume that the schedule is as follows. We put variables A, B, C and D onto the bus in time step 1. We put variables B and E onto the bus at time step 2, and we put variables C, B, F, G onto the bus at time step 3. Because the maximum number of variables that are put in a single time step is 4, we at least require 4 buses, right? And let us assume an example bus allocation here. So in these 4 buses that we require, let us assume that bus 1 has been allocated variables A and G, bus 2 has been allocated variable B, bus 3 has been allocated variable C, and bus 4 has been allocated variable D, E, F. Now suppose with respect to bus 1, we see that at time step 1 variable A is in the bus, at time step 2 also variable A is in the bus, and at time step 3 variable G is in the bus. We see that between time step 1 and time step 2 the variable on the bus does not change. So if the data in A does not change between time steps 1 and 2, the power cost incurred will be low. Now therefore the objective is to keep the same variable onto the same bus line as long as possible, and this is an example allocation. So we can find out an allocation such that the changes in variables on the bus lines is minimized. We will obtain a minimum cost allocation for a given set of bus lines, and this will provide a good allocation in terms of power as well. Thus, with this basic understanding of power hour synthesis, we come to the end of this module.